So in this presentation, we are going to investigate an inverse optimization problem. Specifically, we're going to look at an example, and that example is the 0-1 knapsack problem, the inverse knapsack problem. First, I'll go over the forwards knapsack problem, the traditional one. Then I'll explain what the inverse knapsack problem is. And finally, I'll present an algorithm for solving the inverse problem with some small proofs. I'm not going to go through the proofs, but they'll be there. So just a quick refresher on what the forwards knapsack problem is, the 0-1 knapsack. Suppose you've broken into some house and you have 4 things displayed in front of you. Each of these things has a different price and they have a different weight. You as a robber can carry up to some capacity of items, and you want to select the optimal combination of items to take home the most money without exceeding your carry constraint. So to write this mathematically, there are n items in front of you, and each item has a value vi and a weight wi. Along with that, you as the robber, you have a maximum carrying capacity c, and your objective is to maximize the total value of the items you take home. So we're going to introduce some decision variables, some binary decision variables, xi, where I is from 1 to n. And if you set xi to be 1, that means you want to include item I inside your knapsack. And if it's 0, you don't include it. So steal v, no steal. So in total, the problem is written as we want to select the maximum binary vector x such that the sum of your take-home values is greatest, subject to the constraint that the take-home weights don't exceed your capacity. And this constraint here is just saying that your xi is 0 or 1 only. So we'll just do a quick example. So try and think of what the solution to this might be. So you have a capacity of 6, so you can take home up to 6, so the sum of your take-homes must be less than or equal to 6. The value of the items in front of you are displayed here in this v vector, and the weight of the items is displayed in this w vector. So the full problem is specified here. Okay, so just have a think maybe which items you would want to take home to maximize your value. Shouldn't be too bad. So one idea could be you could take home just the first item. You certainly can do that because it only weighs 6 and that's less than or equal to 6 your total take home, and you'll get 7 value for doing that. Maybe another idea is you could take home these last 2 items. That also adds up to 6, and in total that would gain you 4 plus 3 value, 4, 5, 6, 7. But it turns out that the best decision is to select these middle 2 items, in total only using up 5 of your 6 total capacity, but taking home 9 value. Okay. So one thing worth highlighting here is what I'm going to call the feasible set for the forwards problem. And so this set x here is the set of all binary vectors which are feasible, so that you could, in theory, take those items home. They might not be the best choices, but you could. They satisfy your capacity constraint. So if we have one of these feasible sets x, and we have a value vector, aka a price for every single thing in front of us, then that actually fully specifies the knapsack problem. Because what you can imagine is we have a really naive brute force algorithm which simply loops through every feasible vector and calculates the total take-home value of that feasible vector, and then we simply select the vector in the set x which has the maximum take-home value. So at a high level, what the knapsack problem is we provide this feasible set x, we provide a value vector v, and as an output, we calculate this optimal choice binary vector, like what things we're going to take and not take. In the inverse problem, all we're doing is we're changing which thing is unknown. So we still have our forwards feasible set. So we know basically the weights of the different things and what the robber could take if they wanted to. But now we actually know what the robber did take. So we have that final result, but we don't know what the price of the different things were. And that's what we want to figure out. We want to find a v vector which makes this like equation, air quotes, this equation consistent. So just a quick aside about feasible sets. It's going to be a little bit confusing because we now have two feasible sets. We have the feasible set for the forwards problem, which is the set of all possible x vectors which satisfy the capacity constraint. It's all the possible choices where you aren't overburdened. And we have this inverse problem feasible set as well. And what this is this is all of the value or price vectors which do make this equation consistent. So it's the price vectors which cause x naught here to be the optimal choice by the robber. And there may be many of these. In fact, there are infinite. So sort of to paint the picture again, what we have is we're now playing the role of the detective. The robber has already broken into the house and they've already stolen some items. And we observe that as this vector x naught. What we also see, or we also know, is we know how much the robber can carry, and we know the weights of the individual items. The question we now have is, how did the robber value these items at the time they broke into the house? Find a consistent valuation for that. So, written mathematically, we want to find a value vector v such that when we plug this value vector into the forwards knapsack problem, when we give all of these things that price, the optimal value the robber could get is equal to the value the robber would get if they took home the items specified by x naught. You can pause and think about why this is the right constraint, but I do promise it is the correct one. We also have a non-negativity constraint, but that's not super important to the understanding of the problem. So if you think about it, there's actually infinitely many valuation vectors or price vectors which actually satisfy this constraint problem. So for example, there's a lot which are really degenerate, like they're bad value vectors. For instance, I could price everything as 0, and then anything the robber does is optimal. It doesn't matter what they do. They're all equivalent decisions, steal or no steal. So in order to select a particular v, a particular price vector out of this space of infinite possibilities, what we're going to do is we're going to add some additional information. We're going to want to select a value vector that's close to some existing estimate. So say we have some price estimate y for the different items, and we're going to select a value vector that is close under the infinity norm to that estimate. And I'll just write what this infinity norm is. It's the max over all I of vi minus yi. So it's the kind of like the maximum divergence between these two vectors. So we want to select the value vector which minimizes this divergence, subject to this inverse feasibility constraint, and also that our value vector is integer valued, non-negative. We call this the inverse knapsack problem in the infinity norm. You can imagine we could do different ideas here. We don't have to do this. This is the one we're going to go with. So how do we solve this problem? Well, the main thing is that the sketch of the algorithm is we'll start with some infeasible but very, very optimal under this distance v naught. And we're going to define a sequence of vectors, v1, v2, v3, da 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 da, where as we go up, we're getting further and further away from our y vector, but we're getting more and more feasible in some sense. We're going towards the feasible set. And we'll have this interesting property that we'll have this region of infeasibility, and then we'll step into this region of feasibility, and then from then on, everything will be feasible. This is how we'll define our VKs. And what we're going to do is we're actually going to perform a binary search for this lowest feasible VK. And this one will be our optimal price vector. So we might start here and we'll bounce around, and eventually we'll land in our optimal V star. Okay. So specifically to define VK, it's written using this formula. It's the max of 0, yj minus k, when our x0 vector is 0, blah, blah, blah. I think it's much easier to understand what a VK is with a concrete example. So suppose our x0 vector that we want to induce as the optimal choice looks like this. It's select the first item and also the fourth item. Now y vector, our existing estimate of the prices, looks something like this. We have our weight vector that looks like this, and our capacity, which is 8. Okay, so our sequence of VKs, we start, so V0 starts with the y vector. And you can see that the distance from the y vector to itself is 0. And if we plug this V0 into the forwards knapsack problem, what we will see is that it will not produce this as the optimal decision. It will produce something else. So we'll label this as inverse infeasible. So it's infeasible in the inverse problem. So then V1, what we do is everywhere we see a 1 in our x0 vector, we'll increase it by 1. And everywhere we see a 0 in our x0 vector, we'll decrease by 1. Okay, and in total that changes our infinity norm by increasing it by 1. And we simply run the forwards knapsack problem again, we check, still infeasible. Okay, and we just like iterate this procedure. One thing worth noting is that when we get to a 0, and then we go up again, we don't go negative, we sort of just stay locked at 0. And in this equation, that's what this max of 0 here is doing. Okay, and that just prevents our VK from becoming negative, which is one of the constraints. Okay. So the intuition for what's going on here is we have some space of possible V vectors, right? You could select any price vector and it's going to live in some high dimensional space, 4-dimensional space in this case. And so what we're doing is we are starting at some position y with V1, or actually this should be labeled V0. And as we increase k, we're kind of stepping closer into the feasible region. And once we're in the feasible region, we'll actually stay there forever. Okay. So in order to prove that this idea sort of works, is we need to prove that there exists an optimal solution of the form Vk for some k. And we also need to prove that if Vk is feasible, then everything following it is also feasible. So we need this like pattern to hold. And we need to show that there is an optimal Vk. So this thing is inside your list. This lowest one. Okay. So I'm not going to go through the proofs in detail. I'll attach a PDF with this full document so you can have a look yourself. But sort of outlining, the existence proof is done in 3 steps. First, we show the existence of an optimal V star, and that satisfies some desirable property. We show that there exists a solution, an optimal solution to the inverse problem with some special property. Then what we do is we select or we choose a k based on this special V star we've found. And then we'll show that VK is optimal for the inverse knapsack problem as well. So we start with V star, we create K, then we have VK, and we prove that VK in this case is optimal. Okay. Skipping through all this. The next part is we need to show that we have this property that once we are feasible, inverse feasible, everything after will be feasible. So you can show that. And then also one interesting thing we have to prove as well is we need to define and show that there is an upper bound on K. That is, if I come over here, there is some point we know a priori at the very start, before we even start checking things, we know that there's some K that our actual optimal lives below. So in this case, our optimal K was 3. We want some upper bound, for instance 6 here, that we know that our optimal will be below, less than or equal to. So intuitively what this upper bound will be is it's going to be the value of K such that you have non-negative or positive values in all of your entries where your x0 is 1, and you have zeros everywhere your x0 is 0. And so what this does is it's just saying your robber only gains from selecting like these entries, and they gain nothing from selecting these. So obviously the optimal will be to pick those, which means it's inverse feasible. Okay. So we scroll back down. The point of this upper bound, though, is because without it, what we have is we have this finite sequence of infeasible solutions, V0 through Vk star plus K star minus 1, where K star is our optimal. And then we have this infinite sequence of price vectors, which are feasible. And if we want to perform a binary search, we actually need a lower bound initially and an upper bound initially. Otherwise, we're not going to be able to sort of cut down the search space. So by finding an upper bound, we enable the use of a binary search. So we start with a lower bound here, we start with an upper bound, and then we find some point halfway between them. It'll be over here, let's say. And we check by running the forwards knapsack problem. Is this, and we check, is this like inverse infeasible or inverse feasible? Does it induce x0? And in this case, it won't induce x0. So what we do is we will delete this lower bound and we'll move it over here. So this is the new lower bound. And we'll pick a point in between these, your lower bound and upper bound. In this case, this value or price vector does induce x0. So what we'll do is we'll reduce the upper bound to here, and then you'll pick something in the middle, and you'll keep hopping backwards and forward until your lower bound and upper bound both settle on the true optimal value right here. Okay. So that's really the whole algorithm, written out using some like slightly more technical looking or program looking language. We have something like this. We initialize our lower bound K to 0, and our upper bound to this specially chosen K max. Okay. And then just while our lower bound is not equal to our upper bound, so while we haven't converged, we pick the middle value between our lower and upper bound. We calculate our VK at that position. We run the forwards knapsack problem to get the total value achieved, or the optimum value achieved using that price vector. We then want to see if this optimal value is equal to the value the robber would get if they used their x0, their true decision, what decision they actually made in practice. And if they are equal, then this problem is inverse feasible. So we decrease the upper bound to K. And if the problem is inverse infeasible, then what we're doing is we're increasing the lower bound to K plus 1. Okay. And then finally, once this is all converged, we set our optimal V star equal to VK, and we return that, so our optimal price. And that's it. So just a quick complexity analysis of this code. Line 6 here requires us to run a full knapsack forward problem. And that's known using dynamic programming. We have like a time complexity of NC, where C is the capacity of your knapsack. So pseudo-polynomial. And then we have this outer loop here, this binary search. And this binary search is searching over Kmax items. I'm not sure why this is M here, I should say Kmax. And the binary search will take log of that number of items time to converge. So in total, we have this NC times by log Kmax. And that's the time complexity for the inverse 0, 1 knapsack problem. Hope you enjoyed.